Now, just to see here, definition of a group is G star is a algebraic structure. G is non-empty. Star is a binary operation. Then it has to satisfy closure axiom for A comma B belongs to G, A star B belongs to G. Associative law, then A star B star C equal A star B star C belongs to G for A comma B comma C belongs to G. Existence of identity is for the register element E belongs to G called the identity element such that A star E equal to E star A equal to A, then that will be called as the existence of identity. And similarly here for A belongs to G, there exists A inverse belongs to G such that A star A inverse equal to A inverse star A equal to E, then that will be called as existence of inverse. If the G star, that is the algebraic structure with the four properties, it is satisfied, then that will be called as a group. And then here you see, in addition to the above four properties, if it satisfies the commutative law in the sense, the meaning of that is for A comma B belongs to Z, A star B equal to B star A, there that is called the commutative law. I have taken four properties that is called the group. In addition to that, if it satisfies the commutative law, then that will be called as abelian group or commutative group. Okay, that means you see abelian group means it has to satisfy five properties. Already I have taken the four here. You see closure, associative, existence of identity, existence of inverse. Along with that, if it satisfies commutative law, then that will be called as a commutative group or abelian group. Now we will go for the definition of the semi-group. This is same. The algebraic structure G star, G is non-empty, star is a binary operation. If it is called a semi-group. Why means you see if it satisfies closure axiom, and then associative law, then that will be called as a semi-group. You see, already what taken here. The group itself is a semi-group, but semi-group need not to be a group. Is it not? The first two properties is satisfying, therefore group itself is called a semi-group. That is, if G is a group means that will be a semi-group also. But if it is a semi-group, that need not to be a group. Then here you see the definition. If the number of elements in a group is G is finite, then G star is called a finite group. Otherwise, it is called infinite. Just remember here, G star is an algebraic structure. If G contains the finite number of elements, then that will be called as finite group. If it contains the infinite number of elements, then that will be called as infinite group. Now, the next one, the number of elements in a finite group is called the order of the group. That means how many elements, you see order of the group in the sense, here G must be a finite group. Finite group means the values also you get order of G, it will be, you see the number of elements in a group is called order of the group. It is denoted by O of G. Then here you see the infinite group is of infinite because the number of elements is not countable. Infinite is there, that's why that is called infinite order. Now here for A star B is denoted simply as AB in entire discussion. In entire discussion. Okay, properties of the group. Here already we have studied the properties in case of wire classes. The same we are recalling one more time. Now the identity element is unique. The second one is here. The existence of inverse is also unique. That unique in the sense there will be only one option. There is no other. There is no option here. Unique means only one existing. That is called a unique. Okay, identity element is unique, and the inverse of an element is also unique. Now inverse of inverse is the same element you are writing here. And here you see the reversal line in groups. So already you know AB inverse equal to B inverse, A inverse, B inverse, A inverse. Okay. Now the next one is in a group G star, AX equal to AY, then X is equal to Y. Just here you see, if you operate A inverse on the left hand side, you will get here A inverse AX. We are getting here A inverse A is E into X is X. Similarly, here also A inverse A is E into Y, that we are quoting here X is equal to Y. Similarly, here also for X A equal to Y A, if you operate A inverse on the right hand side, you will get here X A inverse equal to Y A inverse. A inverse is E. According to the existence of the identity element, we can write X into E equal to Y into E, you can write. That's why here they are written X is equal to Y. That is nothing but this is left cancellation law. Here you are writing this is left cancellation. First one is X equal to A Y is the left cancellation law. That implies X equal to Y. X equal to Y A, that implies X is equul to Y. That is the right cancellation law. Just you remember here. left cancellation law, x equal to ay means we are getting x is equal to y, x equal to y means we are getting x is equal to y. Of course, here the next one is in a group G star, there are two elements a comma b belongs to G. There exists x belongs to G such that ax equal to b implies x equal to a inverse b. And similarly, here also we are adding the same one more property is there. There exists y belongs to G such that y equal to b implies y is equal to b inverse. Y is equal to b inverse. Okay. Now here for any two elements a comma b belongs to the group G, a b square equal to, these are some of the properties we are already learned in the previous classes. Same once again they are given here. Here the next one example. We will see the examples of the group. Already you know what is set. Z means set of integers is there. Here Z plus is a group because you see already are taken group in the sense it has to satisfy four properties. One is the closure, associative, then identity, existence of identity, existence of inverse. Then that will be called as a group. Here Z plus satisfies all those four properties. That's why this is called as a group. Okay, this is an example for group, or this is, you can say that is a group itself. Now Q plus is also satisfying. Already you know Q means set of rational numbers is there, and R plus is also set of real numbers is there, and C plus in the sense set of complex numbers. Already you know Z is the set of integers, Q is set of rational numbers, R is set of real numbers, C is the set of complex numbers.
అందులో ఏమేమి కనపడుతున్నావు చెప్పు నాకు. ఇది కాదా?
Who is that? Okay. Now here n plus is there. Here any set of natural numbers is an infinite semi-group and not a group because you see n plus satisfies two properties. One is the closure law and another one is the associative law. But it is not satisfied the identity element because already you know in case of plus 0 is the identity element you are getting normally. But here in the set of natural numbers only the counting numbers you are taking. There is no 0. That's why this is called set is not containing the identity element. Similarly, inverse also it is not possible because you see, if you take 2 belongs to n, if you write here 2 into 1 by 2 that is equal to 1, 1 is the identity element you are getting here, but 1 by 2, 2 belongs to n, 1 by 2 does not belong to n, that's why n plus is not containing the inverse. Here also 0 is not containing, inverse also not existing, that's why this is called a semi-group. That was only the first two properties. Similarly, the remaining thing. N dot is there. N dot means here you see this is a semi-group with identity element. Here also the inverse is does not existing and only the here you are seeing the identity element is existing here. Z dot is also not a group because you see for any element minus 2 belongs to Z. If you take minus 2 into some minus 1 by 2 that is equal to 1 you are getting, but minus 1 by 2 is a fraction that is not belongs to Z. That's why this is also not a group. And here 1 omega omega square 1 minus 1 dot, these are all finite abelian because you see what are the how many elements are there in the 1 minus 1 I 1 minus 1 comma dot means here you see this is the group containing the two elements are there, only the finite number of elements are there, that's why this is called a finite group. And then here you see abelian group, this satisfies the already are taken, you have seen in the previous case abelian group or commutative group is 1, it satisfies 5 properties. So group properties are 4, and if it satisfies the commutative law, then that will be called a abelian group. Here it's here also the same. How many elements are there in a group? 1 omega omega square is there. That is the here you see 1 omega omega square, 3 elements are there. That is the finite one. But here you see n dot is not the finite one. Here you see n what are taken z plus. This is not a finite one. This is an infinite group. Z plus is infinite group is an example. Also q plus r plus they are also infinite group. But here you see the number of elements are finite one. 1 omega omega square is there. 3 elements are there. Order of g equal how much? That is equal to 3 elements are there, which is equal to 3. Similarly, the fourth roots of unity. Because already know 1 omega omega square are called the cube roots of unity, and here 1 minus 1 I minus I, they are the fourth roots of unity, and it satisfies here, it satisfies the only the four properties. That's why this is called a group. Okay, now we'll go for the subgroups. Okay, we'll go for, and just to remember here, Z plus means whenever you take the plus sign, the identity element is 0. Identity element is 0. And whenever you take the dot, here you see the identity element is 1. Okay, you see when you are taking the plus sign, you are getting the identity element as 0. Whenever you are taking the dot as the binary operation, the identity element is 1. That you keep it in mind. Okay, inverse there is no bother about that one, but here you see. Okay, now we'll go for the subgroups. Already you know the subgroup. Okay, you see the definition that G be a group under the binary operation star. That means G star you can say here. H be a non-empty subset of G. Then H is called a subgroup of G if H is a group itself under the same binary operation star. Now here you see G star is a group. G is non-empty and star is a binary operation. You see H is a subset of G. One condition is H must be a subset of G. That is for subgroup. And one more, you see H itself is a group. H itself is a, then only that will be called as a subgroup of the G star. You see here, H is also the binary operation star, and G is also containing the binary operation star. Then only it is called as a subgroup of G. H is a subgroup of G. Okay. Now here, so every set is a subset of itself. Okay, that is obvious. If G is a group, then G itself is a subgroup of G. That is obvious. Also, a subset containing the identity element alone will also be a subgroup of G. That is also identity element means it satisfies all the properties of the group and it is a subset of G. Therefore, that is called subgroup of G. Now, these two subgroups are called trivial or improper subgroup. What are those two groups means? The group itself and then the identity element. Those two are called the trivial or improper subgroup. You remember this because this is asking. There is a point of asking the competitive exams. You remember this. Okay. First one is what? First one is the group itself is the group itself is a subgroup and the identity element containing that group is also a subgroup of G. Those two are the trivial groups or improper subgroups. Now we'll see the next one. If there is any other subgroup of G except the group itself or the group containing the identity element alone, it is called a proper subgroup. This is also you see already taken trivial means the group itself and the identity element. Other than those two is existing. That subgroup is called proper subgroup. You see here R plus what is R here? Set of real numbers and C is a set of complex numbers. Okay, because you see complex number you can express in terms that you can express as a real number. Okay, because a plus ib format you are getting ab belongs to r. If you put b equal to 0 you will get here the set of real numbers. That's why r plus is a subgroup of c plus, because r is the elements of that c plus you can express as elements of r. Therefore this is a subset and it is a group. R plus is a group, C plus is a group, and then here R is a subset of C. Therefore, this is a subgroup of C. Already are taken there. You see, first it must be a subset. Okay, first condition is it must be a subset, and then the binary operation is same. And then you see, first one for the Q plus must be a subgroup and R plus must be a group. Then only the Q plus is said to be a subgroup of R plus. Okay, those three properties. What is the first one here? The first one is it must be the same binary operation must be same. Here plus is there, here plus is there. Okay, and then here you see the elements of R is subset of the elements of C. Then R is the subset of C you are getting here. Plus is the binary operation, and then R is a group under plus, and C is a group under plus. Then only R plus is said to be C plus subgroup of C plus, because we have to satisfy those three properties. One must be a binary operation must be same. Second one is that is a subset of C, R is a subset of C, and third one is R is a subgroup under plus, C is a subgroup under plus. The same is applicable for the remaining. And here you are writing N plus is not a subgroup. Why you are not writing? Why you are saying N plus is not a subgroup? Because you see n plus, if you take the set of natural numbers is whenever I am already told in the previously, you see plus means you got the what is the identity element? 0 you have to get, but in the set of natural numbers there is no 0. That's why this is not a subgroup. Of course this is a semi group, and n plus is a semi group. Okay, now here also minus 1 1. This is also finite order group. This is the finite group is there. This is here you see minus 1 1, the number of elements are 2, and the dot is there, and minus 1 1 is subset of minus 1 1 minus I. This is a subset, and the binary operation is same. And then this is a group under dot, and this is also a group under dot. Therefore this is a subgroup of 1 minus 1 1 minus I. So of course there is the 4 roots of unity. Now we'll go for the necessary and substantial condition for a subgroup. Now why we are doing this, the necessary and substantial condition means In some of the cases, you are not proving directly. You are not proving directly. Instead of proving the group, already you have taken that group means you have to satisfy four properties. Along with that, instead of proving that property, if you prove this statement, then you can. There is no need to prove the previous one. What you are taking the four properties is not necessary to prove. That's why here you are taking some of the properties. Okay, this you are using in the problems. Okay, this you are using in the problems. Okay, now the necessary condition, necessary and sufficient condition for a subgroup. The statement is a non-empty set H of a group G is a subgroup of G if and only if A comma B belongs to H implies A B inverse belongs to H. What is that? Here G is a group, H is a non-empty subset of G, and then if and only if means we have to prove here if P then Q and if Q then P, then only it is said to be if and only. That means to and fro. That is to and fro. If it is satisfied, then that will be said to be the AB belongs to H is implies AB inverse belongs to H. That is to and fro is the condition. Okay, that's why this is called necessary and sufficient condition. Now, first suppose that H is a subgroup of G. Now, if P then Q we are proving here, H is a subgroup of G that we are taking, and we have to prove AB inverse belongs to H. Now, just to remember here what we have to prove. What we have to prove means we have to know what is given and what we have to prove. Here, subgroup is given. Subgroup means H is a group under the same binary operation of star dot plus whatever it may be, the same binary operation under G. Now B belongs to H. Okay, already are taken H is a subgroup of G. H is a subgroup means we are already taken H is a group. H is a group and it is non-empty and star is a binary operation in H as well as G. Now here you are taking one element of B and here you are writing B inverse belongs to. Why you are writing B inverse belongs to H? Because you see H is a subgroup means it is itself is a group. Group means satisfy all the four properties. Now B belongs to an element of H means the inverse is also belongs to, because there is a group means the inverse must be existed and that means belongs to H. Now already you know A belongs to H. One element is belongs to this, B inverse also belongs to H. Now if you combine that, why you are combining means this H is a group, subgroup means it is a group, and if you A into B inverse is equal, if it implies here A B inverse belongs to H, because the closure law you are using here. Closure law, A is an element of H. This is also an element of H. If you break the product, that is also belongs to H. Okay. Now, what you are taken here? AB belongs to H you are taken, and we are proving AB inverse belongs to H. Okay. That is somewhat here group by taking that group condition of H, you are proving this is a AB inverse belongs to H. Now the reverse way, that is, if AB belongs to H, AB inverse belongs to H, H is a non-empty subset of G, then we have to prove H is a subgroup. We have to prove H is a subgroup. Here, just you see conversely, suppose that A comma B belongs to H. Suppose that A comma B belongs to H. A comma B belongs to H. Now here AB inverse belongs to H you are writing. AB inverse that is already given. If P then Q is over. By taking this AB inverse belongs to H, you have to prove H is a subgroup of G. You have to prove. Already H is a subset of G. There is no need to prove there. And then here and here you see here AB inverse belongs to H you are written, and by using this you have to prove. Now actually to prove this is a group, it has to satisfy four properties. Here we are not proving the closure law and closure law, as well as here we are not proving the closure law as well as associative law. That is obvious here. Okay, two elements means here that is obvious. Just you have to show the inverse element and then identity element is existing, then you can say that is itself is a group, because H is a subset of G means closure and associative law. There is no need to prove. That is obvious. There is no need to prove that you cannot directly, since it is a subset of G. The closure associative law is existing already. Now here to prove AB inverse means what you have to prove here. Here if you take A comma B belongs to H means you are writing AB inverse belongs to H. You have to take the convenient one. Here A belongs to H you are taking, and you are writing here A inverse belongs to H. That means A inverse is what? Dot is, of course, here dot is not written, that is understood. A dot A inverse, that is multiplication is there. A into A inverse is E belongs to H. Okay, E belongs to H, therefore the identity element is existing. Now by using the same, here E belongs to H you are writing and A belongs to H. This is by convenient, there may be you may ask the question here, E, why you are writing this means by using somehow here AB inverse belongs to H, you have to prove the inverse is also belongs to H. Here you are taking E belongs to H, A belongs to H. Now by applying this, you see first element A is equal to E, E A, the second one is A, E A inverse belongs to H, A inverse, you see here A belongs to H means the inverse is also belongs to H. That means here you see you are getting here the identity, existence of identity, here you are getting the existence of inverse, and here you are writing the H is a subset of G means already I am told to you further on associative law is as usual. Now H is a subgroup under the bind operation defined because all the four properties satisfied. That's why this is called H is a group under the binary operation as defined in Z. Now what we got, H is a subset and H is a group, and then you can say what you can, the same binary operation is there, therefore H is a subgroup of G. Okay, yeah.